Prime ideals are important because of this theorem. Let R be a commutative ring with unity, and let A be an ideal in R, an ideal of R. There's an if and only if statement you can make about the factor ring. Then the factor ring is an integral domain. And when you see that phrase integral domain, always try to quickly remind yourself what it means. It means it has no zero divisors. It's going to be a commutative ring with unity with no zero divisors. If and only if A is a prime ideal in R. Let's think about the idea of the proof. First, let's think about this direction. Assume this factor ring is an integral domain. It's got no zero divisors. Show that A is a prime ideal. I guess we'd have to use the definition of a prime ideal somehow. How do you start that? Suppose you got a product being in the ideal. We must show, our favorite phrase, we must show A is in the ideal or B is in the ideal. We've got to relate this to the factor ring somehow. It's an integral domain. It's got no zero divisors. How in the world can we relate it to the factor ring? Could take some experimentation. The key thing to realize is, since you're supposing AB is in the ideal, if you consider the left coset with AB as the representative, so this is a bit of scratch work right here. AB being in A implies the coset with AB as the representative must equal A itself, right? It's sucked in. That again is nothing more than just property of cosets. In group theory, we wrote that property as AH equals H if and only if A is an H. That was the way we wrote that, this exact same property in group theory. Different notation, a plus sign. There was no plus sign over here. But it's the same idea. I did say back in chapter 7, properties of cosets are key to this course. We're seeing it right now. Well, what does this mean? Well, the left coset, A itself, is the same as 0 plus the left coset. This is the zero element of the factor ring, the additive identity. This is the zero element of the factor ring. Interesting. If I suppose a product is in the ideal, then the corresponding coset with that thing as the representative is the trivial ideal, the zero of the factor ring. Think about what you want to show. You must show little a is in capital A or little b is in capital A. In other words, relating it to factor rings, you must show little a plus capital A is the zero, or little b plus capital A is the zero of the factor ring. Those would be equivalent. How to do that? You got to use the fact that this is an integral domain somehow, that you're assuming that. How in the world? It's not clear. Until a little bit of experimentation, maybe a little bit of coffee, maybe a little bit of sleep, helps you realize, you know, another way to write this thing is as the product A plus capital A times B plus capital A by definition of coset multiplication, right? You'd multiply these cosets by multiplying their representatives. You don't FOIL it, right? There's no A squared that shows up anywhere, no capital A squared. You just keep the plus A there as a placeholder, kind of. You just multiply the coset representatives. So since this is true, that means this thing would also be equal to the zero element. Product of two things being zero. That's related to the definition of zero divisors. If there are no zero divisors, The only way for that to happen is if one of these or one or the other is zero. The fact that the factoring is an integral domain, ID, along with this implies either this is the zero element or that is the zero element, which implies either A is in capital A or B is in capital A. Done. The other direction is to show that if A is a prime ideal, then the factoring is an integral domain. We just showed if the factoring is an integral domain, then A is a prime ideal. Now we need to do it the other way around. Suppose A is a prime ideal of R. Show the factoring is an integral domain. It's certainly a commutative ring with unity, because R is a commutative ring with unity. The factoring is going to inherit that pretty trivially. What's the unity? Certainly a commutative ring with unity. What is the unity? How about 1 plus A? If 1 is the unity of R, form that coset, 1 plus A. I mean, that makes sense that that probably should be the unity, and you can check it. You multiply this by any other coset, you're going to get that other coset by definition of coset multiplication and definition of unity. So all that's left is to show the factoring has no zero divisors. So once again, you're supposing, suppose you've got the product of two things in the factor ring equaling the zero element A itself, and show that one or the other of these is the zero element. The only way for the product of two things to be zero is if one or the other of the elements is zero. That means it's got no zero divisors. That means it's going to be an integral domain. What do we need to use? We need to use the assumption that A is a prime ideal. This should feel at first glance like we're just going to reverse what we did before. And essentially that is the case. Go ahead and multiply these out. By definition of coset multiplication, it's that. We're saying ultimately, since we're supposing it, that this equals that. It's the trivial coset, which means AB is in capital A. But I'm assuming A is a prime ideal of R. By definition of prime ideal, that means little a is in capital A or little b is in capital A. Which means little a plus capital A is capital A, or little b plus capital A is capital A. One or the other is the zero element of the factoring, and that means we're done.